Let me share the slides. All right, so could you please confirm if you can see the slide on the screen?
Yes, doctor.
Right, thank you. Okay, yesterday we stopped at compensated semiconductors, right? And we've discussed a little bit on the concept of compensated semiconductors. And we learned that a compensated semiconductor is a semiconductor that contains both donor and impurity acceptor, donor and acceptor impurity atoms. Or we have both types of dopants in the same region or in the same lattice, okay? So, for example, yesterday we discussed about you can compensate a semiconductor by reversing the polarity of that semiconductor, essentially by reducing the majority carriers in the semiconductor material. For example, we have been discussing about introducing dopants into the silicon lattice where the silicon started off as an intrinsic semiconductor or undoped semiconductor, and you keep adding on impurities from either group 3 or 5 in order to make the silicon more p-type or more n-type, either one, right, respectively. On the other hand, when you talk about compensation or compensated semiconductors, you have to start off with a polarity of a semiconductor material. For example, if you start off with an n-type silicon wafer, in this case, for example, you can compensate the semiconductor by incorporating p-type dopants into the silicon in order to effectively reduce the majority carriers in the n-type silicon by adding more and more opposite carriers, in this case, more holes to the existing electrons, right? On the other hand, you can also do the same thing for a p-type silicon as a starting material, for example. You can actually compensate that p-type material by incorporating more and more phosphorus from n-type, from group 5 to make it more n-type. Well, when you started the incorporation of the phosphorus, you don't actually make it n-type yet because you are just reducing the level of majority carriers in the existing material where the existing majority carriers are holes in the p-type. So that's why for this particular concept, you really have to understand the concept of majority carriers and minority carriers first, right? So we've discussed yesterday that, and beforehand as well, that the majority carriers in the p-type are holes and the minority are electrons, whereas in n-type, the majority are electrons and the minority are holes, right? So we have also learned before that you can tell the level of majority carriers in a semiconductor material by looking at the level of ND or NA, because we assume N can be approximated to the value of ND, assuming 100% ionization, and P can be approximated to the value of Na, assuming 100% ionization. So since both Na and Nd are typically larger than Ni, for silicon is 10 to the 10, then you can just omit the magnitude of 10, 10, 10 to the 10, because 10 to the 15 or 10 to the 16 is like 5 or 6 orders of magnitude higher than 10 to the 10. And that will make the 10 to the 10 negligible in the final value, right? So that's effectively n equals to nd and p equals to na. So that's how you can tell the level of majority carriers. And we've also learned before that the moment you know your majority carriers, the level of majority carriers, you can then tell the level of minority carriers. Okay, how do we do that? You know the majority carriers. How do we then tell the level of minority carriers? Let's recap a bit before we move on. You know the majority, you don't know the minority. How do you know the minority then? Anyone? Any volunteers? Alisa? You know the majority carriers. How do you then tell the minority carriers? The value of minority carriers. Yes, depends on which is dominant, of course. Now I'm asking about, you know the level of the value, the level of majority carriers. How do you then tell the level of your minority carriers? Anyone? The level here means the value, the figures, the exact concentration. How do you tell? Najia? Najia, my FYP student. Yep. Mass law equation, law of mass action, right? Law of mass action. So can you state the law there in the chat box? Can you state the equation, Bala? What is the exact equation they use for this law? Law of mass action. So please write down in the chat box. Is it NP equals to NI? Anyone would like to? Okay. N times P equals to Ni squared. Okay. N times P equals to Ni squared. So if you know, say if you're working on N-type silicon, so you know the value of N, isn't it? Because N is equal to Nd, therefore you know the value of N in this particular equation, because N is the majority carriers. Okay, you can then calculate the value of P by dividing Ni squared over N, and you're gonna get your P. So let's just test. If your Nd is equal to 10 to the 16, what is the value of your minority carriers? You're working on silicon with N-type 10 to the 16. What is the level of your minority carriers in this silicon? Let's just do a quick math without pressing calculators. Anyone? You're working on N-type silicon. The doping level of 10 to the 16. What is the value of your minority carrier concentration? So that's the question. Anyone? Is it 1 minus P? Which equation are you using, Zuki? You have to go back to law of mass action, yeah, Zuki? So go back to NP Ni squared, right? NP equals to, yeah, I said right. Saya tulis balik ke sini ya. Hold on. NP equals to Ni squared, okay? So go back to that. Jump mouse is not moving. So N times P equals to Ni squared. You're working on N-type. You're working on N-type 10 to the 16, right? So your N-type is 10 to the 16, isn't it? Kadang-kadang this simple thing, we have to get it clear first before you move on to some other calculations. So you're working on N-type silicon 10 to the 16 doping level. Okay. So what is the, okay, let me just ask you an obvious question first before we come back to that. you are working on silicon, N-type silicon, doping level 10 to the 16. What is the level of majority carriers in your silicon? What is the level of majority, or what is the doping concentration, or what is the carrier concentration? Sama dia, the words are different, but then it's referring to the very same thing. What is the carrier concentration? What is the majority carrier concentration in your N-type silicon? Right? Voilà. So you're working on N-type silicon, doping level 10 to the 16. What is the majority carrier concentration in your N-type silicon? Obviously 10 to the 16. So I would like to start with something obvious first. Okay, clear. So everyone clear? 10 to the 16. Okay, ada confusion? Majority carriers 10 to the 16, right? Ada objection? Tak ada. Okay, all good. So now let's move on to the less obvious question, but still obvious, but a bit less obvious than this. What is the level of your minority carriers in your N-type silicon? Tadi Bala dah jawab kan, 10 to the 4, right? Any objection to the previous answers? Previous answer by Bala, 10 to the 4. Bala, can you unmute and explain a bit? How did you get that to the rest of the class?
Using the mass law equation. So
Okay.
like Ni is 10 to the 10. So
Okay.
square that with 10 to the 20.
Okay.
I divide it by 10 to the 16 because it's Np equals to Ni square. So
Right.
the N is 10 to the 16.
Okay.
So when I 10 to the 20 divided by 10 to the 16, it's 20 minus 16. So
Yep.
it's 4. So it's just
Yep.
10 to the 4.
10 to
So
the
P
4.
equals
So,
to 10 to the 4.
right. Okay, good. Thank you very much. So your P then equals to 10 to the 4. Okay. P, let me just write down. P 10 to the 4. Okay. Per centimeter cube. So as Bala explained, P equals to Ni squared over N. N is equal to Nd. Nd is 10 16. Ni 10 to the 10. Square that 10 to 20 over 10 to the 16. So 20 minus 16. Simple math, 10 to the 4, right? So your majority carriers are 10 to the 16 electrons. Minority carriers are 10 to the 4 holes. Okay? Simple aja. Tapi this simple thing pun kadang-kadang we have to get it straight first before we move on to the next. Okay? So simple, right? So if you're talking about majority carriers of 10 to the 15, then you're talking about minority carriers of 10 to the 5. If you're talking about majority carriers 10 to the 14, you're talking about minority carriers 10 to the 6. If you're talking about majority carriers 10 to the 19, you're talking about minority carrier of 10, 10 to the 1, or 10. So bottom line, N times P equals N squared. Okay, you kena campur N dengan, bukan campur lah. You have to campur the order of magnitude ke atas. So just a simple math to get back 10 to the 20 squared, right? Due to the square of Ni. Okay, everyone clear on this? Any confusion still? NP N squared. You're going to use a lot of this when we talk about majority carriers, minority carriers in P-type, N-type, PN junction later on. Nanti kita akan belajar in the next topic. How do the carriers move? Then P masuk N masuk P, apa jadi kat majority, apa jadi kat minority of both sides. And then it's going to get more messy, if you like. A bit messy, okay? You're going to know, you have to get your pillars solid first. These are the pillars, NP, N squared, right? So semua okay, any question on this? No? Cool. Tak ada. So clear NP, N squared. So lepas ni, if you have a question, you have a silicon of 10 to the 17, what are the majority carriers? Senang, 10 to the 17. What are minority carriers? 10 to the 3. Easy peasy, right? Silicon. If you talk about the rest, then might be you have to go back to the Ni value of gallium arsenide or indium phosphide or whatever. But if silicon is here already, right? 10 to the 10, you square, divide by majority, you get a minority, or vice versa. Okay. That's why this is the point that I made last time, when it's a lot easier for you to use Ni equals to 1 times 10 to the 10. Kalau you pakai 1.5 times 10 to the 10, which is equally correct, equally acknowledged, you punya division process will be a bit longer lah, because you need to divide 1.5 with something in front of 10 to the whatever. So you have to then press the calculator. Okay, kalau 1 time is just straightforward. You just have to work on the 10 to the whatever to do the math and get answers, right? Okay, so this is the point. So use 1 times 10 to the 10 instead of 1.5 times 10 to the 10, unless you insist to use 1.5. Up to you, right? Senang, it's a lot easier. Tak payah tekan calculator pun dah tahu jawapan. Right, so getting back to this compensated semiconductor concept, we normally say a semiconductor to be n-type compensated if your ND is your ND exceeds your NA. So that means you start off with NA and then you dope with ND. You reducing the holes in the existing semiconductor material. The moment you hit the point when your ND is more than your NA, you call that semiconductor as n-type compensated. So that's the terminology that we use for n-type compensated. And this is also true for the other way around. If you start off with the n-type and then you introduce p-type dopants to the silicon up to the point when your Na exceeds Nd, you call that semiconductor as p-type compensated. Okay. So kalau you have a question on you're working on p-type compensated semiconductor, so you have to know the sequence already, right? So you start off with the opposite one, but you introduce the opposite polarity, you end up with the opposite polarity being dominant in the lattice, and you call that as compensated. Okay. On the other hand, if you have Na equals to Nd, we call that as completely compensated. Just nice. Na equals to Nd. Kalau dia exceed sikit, dia akan we call that as the dominant carriers lah, Na or Nd, right? P-type compensated, N-type compensated. But if it's completely equal, then we call that as completely compensated. So there's no effective majority carriers, and your semiconductor turns to be intrinsic again, as if it wasn't doped at all. Okay, due to the equal value of Na and Nd on both sides of the equation or together in the lattice. Compensated semiconductors are created quite naturally during device fabrication, as we'll see later on. And I've also explained to you a trick if you don't have any intrinsic wafer to work on and you only have like p-type wafers. To be able to get intrinsic, you can actually compensate that that semiconductor to get to intrinsic by incorporating the opposite dopant by this concept. Okay, you boleh buat. Okay, you can actually reverse the polarity to get back to intrinsic just by manipulating the opposite dopant and incorporating them into the lattice. It can be done. So it's just that you have to incorporate gradually. You have to know what are the levels that you're incorporating, and then eventually you have to do the measurement to show that you don't have any majority carriers in the semiconductor material, and at that point you call that as completely compensated. It can be done. It's just that it's a bit tricky. It's a lot easier to work on an original intrinsic silicon because it's already controlled there to begin with, right? But it can be done. If you have to physically, if you know the concept, if you know how it works, you can manipulate for many things, right? Either it's supposed to be like that or it's not supposed to be like that. So now let's look at the variation of EF with the level of doping. So you can, let's again see the band diagram. Note your EC, note your EV. So this is essentially a band diagram. Nampaknya complicated, but it's actually this, that, and this is your EG. You label again your EV, EC, and then your EF intrinsic is right in the middle because it's supposed to be right in the middle for intrinsic material. For silicon, it's supposed to be 0.56 EV because the band gap is 1.12. So we have discussed before that when you increase your doping level, your EF will change, right? The level of your EF will change accordingly. So for example, if you look at ND for the top part, right? ND x-axis. So we're talking about changing the doping level from 10 to the 12 up to 10 to the 18 on the x-axis. Okay, atas dengan bawah sama aja. Except it's showing the opposite dopants, ND, NA. Right, so the point here is if you increase the doping level, which means going to the right, going to heavily moderately doped, going to heavily doped. So you can see this as moving from lightly doped to moderately doped to heavily doped, going from left to the right. Okay, and as a result, for n-type, let's see n-type first, you can see that your EF, this blue curve or blue line, is actually your EF, how your EF changes over the doping level. So your EF changes to be closer and closer and closer to the EC. So we discussed before that it started off somewhere there, and it's going there, and then it's going there, it's going there, it's going there, right? So just like what we discussed when we talk about degenerate semiconductors as well. So kalau you draw a line of this trend, you're gonna get that essentially, right? So at the, if you see at 10 to the 12, your EF is just above your intrinsic level, right? Just above your intrinsic for your EF, EFI, but at 10 to the 18 is very, very close to the EC, right? Right below your EC. And the same thing happens to your p-type as well. So if you dope your silicon with boron, more and more borons into the lattice, and then you're going to see your EF changes from close to the middle of the band gap, close to the EFI, but it's not EFI. Okay, it's not there on EFI because it's not intrinsic. It's lightly doped 10 to the 12. Okay, so that's why you couldn't start right there because it's not intrinsic. It's already extrinsic. So the moment it's already extrinsic, it has to be either slightly above or slightly below EFI, right? Relative to the doping level. Right, so at 10 to the 18, your EF gets very, very close to the EV, okay? So that's what happens when you increase your doping level in your semiconductor, and your EF will be closer and closer to EC or EV. Right, figure shows your Fermi level as a function of donor concentration N-type and also acceptor concentration P-type at 300 Kelvin. So assuming there's no change in temperature, okay? There's no change in temperature. As the doping level increases, the Fermi level moves towards CB for N-type and towards VB for P-type, okay? Clear. So let's have a look at the temperature variation now. The intrinsic carrier concentration Ni, this one, if you don't, you can discuss this either in intrinsic condition or can be discussed in extrinsic condition, extrinsic N-type or P-type lah. So it can either be discussed in intrinsic or extrinsic conditions. So the intrinsic carrier concentration Ni is a strong function of temperature. Okay, Ni is a strong function of temperature, so that your EF is a strong function of temperature as well. So anyone would like to explain this? Why your Ni or your EF is a strong function of temperature? What's actually happening? Anyone? We discussed this one briefly last time. Kenapa is a strong function of temperature? What your Ni and therefore your EF as well? You can say Ni or you can even say EF. Both are showing a strong function of temperature. Why? Kenapa a strong function of temperature? Yes, depends on KT. We discussed KT last time, right? And we've done the calculation, isn't it? Remember last time we talked about the change of 0.025 or 26 EV, and then you change temperature, and then you're gonna get your new KT 0.082 EV, and your Boltzmann constant remains the same. It's constant K, but temperature changes. So the change in temperature or the increase in temperature causes apa? When you have increase in temperature, what's going to change in the lattice? Ataupun apa yang akan terjadi in the lattice when you increase the temperature or your KT increases? What's actually happening to the carriers? We discussed last time when we talked about Fermi direct distribution function, right? Apa jadi? Remember last time T1, T2? What is the mechanism? What is the exact name of the mechanism? as you increase your T, effectively KT. Anyone? What is the term there? What's the mechanism? What is the physics there? Further, if KT increases, so what also increases? What is the term there? Or mechanism that's happening to the carriers? Anyone? Ready? Ionization increases, yes. What was the name of that mechanism? Yeah, you can also say ionization. The exact one that we discussed in Fermi Dirac distribution function. Mula huruf T. What's the process there, or the event, or the mechanism? Thermal excitation. Yes, that's what. Thermal excitation. Good. Thermalization comes next, right? It's okay. Thermal excitation first. Remember your KT. T0 Kelvin is a step function. T1, then you're gonna get your curve, and then T2, your curve is higher than your T1. You're gonna get your area and the curve and all those stuff for Dirac distribution function. As your temperature increases, your thermal excitation increases as well. So you're gonna get more and more valence band electrons excited into the conduction band, and that's why your Ni, which is effectively the number of bonds broken or the number of electrons excited. Sama kan, kita discuss last time. N equals to P equals to Ni, remember, in intrinsic. So your Ni is actually the number of bonds being broken due to the excitation of the valence band electrons from VB to CB. So due to this temperature increase, you're going to get a strong function of temperature. So your EF will move accordingly as well due to the very same mechanism, right? Temperature increases, Ni increases, and EF moves closer to intrinsic Fermi level. At high temperature, okay, when you talk about temperature, there's a region, there are a few regions that we have to discuss. It's not a blanket answer. We're going to see that later on, right? Okay, at high temperature, material begins to lose its extrinsic characteristics. You started off with extrinsic semiconductor, but at high temperature, the extrinsic semiconductor is going to lose its extrinsic properties. Kenapa? And is going to behave more like intrinsic semiconductor. If you go to high temperature, so let's have a look at this diagram on the left. If you move to high temperature, high temperature means going to the right x-axis. Okay, and look at your Fermi level there. Fermi level is going to change from, so at a low temperature, you're going to get your EF to be very close to either EC or EV, okay, because it is extrinsic to begin with. But at some point at high temperature, if you go to the right, you're going to see that you're going to move closer and closer to the intrinsic, closer and closer to EFI, as if it wasn't doped at all, okay. Maksudnya, you start off at extrinsic. If you heat it up at a very high temperature, it's going to be intrinsic eventually. It can be done as well. Okay, so doping, kalau you dope intrinsic silicon, you're going to get extrinsic eventually. But you can reverse the process by heating the semiconductor at a very high temperature. So you have learned few concepts now, which you can also translate as few tricks. Okay, let's put it like this. You start off with intrinsic semiconductor, then you dope to make it extrinsic, right? P-type, okay, N-type, doesn't matter. You make it extrinsic already. And then how do you make it back to be intrinsic? You can either compensate, kita dah belajar tadi, by reverse doping, if you like, by opposite polarity, incorporation into the lattice, which will make it Na equals to Nd, which is essentially an intrinsic semiconductor, or, yang tu yang pertama, or you can also heat up that semiconductor material, extrinsic, and it's going to turn to be intrinsic eventually. So two ways to be, that you can do in order to make it to be intrinsic again is by compensation doping, and also by heating up that extrinsic semiconductor. You're going to get intrinsic eventually for both cases. Okay. So you can treat these two concepts as a trick as well if you have to somewhere in the future, I don't know. right? So we're going to see later on why is this happening. Kenapa
Doctor.
kau jadi intrinsic? Yep.
Doctor, so when you heat it up, it permanently becomes intrinsic, is it? Or if you reduce by the temperature, it goes back to extrinsic conditions.
Yes, good question. You mean heating up, right? It's not the reverse doping, right?
Yes, I mean heating it up.
Exactly. It's not supposed to be. It's not supposed to be permanent unless you maintain the temperature of the semiconductor material. So it is a very good point you raised there, because if you compensate the semiconductor, it's going to be permanently at intrinsic. I'm going to show you the curve later on. But on the other hand, if you do the temperature, you have to maintain the temperature at steady state in order to maintain the excitation, if you like. Sebab kita dah belajar previously, when you remove the temperature, what happens to the carriers? You impose the temperature, is going to be thermally excited, the carriers. You remove the temperature, you remove the heat, what's going to happen? Tadi Zuki baru mention, right? That word, thermalization, isn't it? So you lose, exactly, you're going to lose your excited carriers eventually if you remove the temperature. So that means it's going to be restored. The original condition is going to be restored. So good points. Good question there. Right. So I'm going to show you the curve later on. How do we then manipulate and by regions and stuff. At a very low temperature, freeze out the curves. At very low temperature, freeze out macam beku lah, if you like, right? The Boltzmann constant is no longer valid, and the equation we derive from the Fermi level position no longer apply. So how do you freeze carriers? Okay, how do you then freeze carriers? Let's see. So this is a freeze out. One region is called freeze out. You can see this curve which shows electron density. You can read the caption here. Electron density is a function of temperature for a silicon sample with a donor concentration of 10-15. So is it N-type or P-type, this silicon? Before we discuss the shape of the curve. So read that caption there. Is it a, right? N-type, isn't it? Because it's ND, okay? And to get clear, N equals to ND, P equals to NA. So donor means N-type. Okay, so you're going to start off with N-type silicon, 10 to the 15 per centimeter cube. So what happens then when you heat up the sample, right? When you apply heat to the sample. So you can compare there. If your temperature is very, very low, apa jadi? Your dopants are not electrically activated. Okay, your dopants are not electrically activated because remember last time we talked about ionization. Who can recall what is the minimum energy level required for our typical dopants to be electrically active? Anyone can recall? X electron volt required typically. X is the unknown. Fada? Lower, Fada. You got your decimals correct. 0.02 is correct, but the first number is not correct. 0.02, 0.02, okay, good for that. 0.02 typical, typical energy level required for you to electrically activate the dopant, and this requires temperature. Okay, this requires heat, at least room temperature lah, for you to have some carriers wandering around and do the conduction, and you become extrinsic. Okay, if you're in freeze out region, they're not electrically active, and therefore they will not contribute to the electron density or effective electron density on the y-axis, and they are not extrinsic, if you like. Okay, so that's why you can see that the extrinsic region here in the middle only start at some temperature where they gain enough energy to be electrically active and to demonstrate the extrinsic properties. Okay, and that will stay for like a couple of hundreds Kelvin. Okay, until at some point you're gonna see that your extrinsic is lost, extrinsic properties is lost, and at this particular temperature you're gonna get more Ni broken. You're gonna get more thermally excited carriers, and at some point you're gonna get both sides of electrons and holes dominant. So let's see the explanation here. At low temperatures, the thermal energy in the crystal is not sufficient to ionize. Okay, this is the point. 0.02 is not there to ionize the dopant impurities present. Some electrons are frozen. You can say frozen if you like at the donor level, and the electron density is way less than the donor concentration, or N that you are expecting is way less than your effective ND that you have put or you've incorporated in the lattice. As the temperature increases, the condition of complete ionization is reached. So you've got this 0.02 at least in order to electrically ionize the dopants, and they now demonstrate extrinsic semiconductor properties. So that means they are there and they are active in the lattice, right? As the temperature is further increased, so we're now talking about going further to the right, the electron concentration remains essentially the same over a wide temperature range, which is this middle region. Okay, this is called extrinsic region as the temperature is increased. However, as the temperature is increased even further, we reach a point, this point there, inflection point if you like, where the intrinsic carrier concentration becomes comparable to the donor concentration. At this point, Ni is equal to Nd. Remember last time when we talked about extrinsic, what is the comparison in terms of the value between Ni versus Nd? What's the notation in between that you have to put here? If you talk about extrinsic, in order for it to be extrinsic, this is all understanding, demonstrating understanding. Upper notation that you have to put in the middle instead of approximately equal here. If you say your semiconductor is extrinsic, what is the sign that you have to put in the middle of this box? Extrinsic. Anyone? Just one sign to demonstrate your previous understanding. Anyone? Come on. Simple ini. You're not comparing on this one now. So what's supposed to be there in the middle here? Anyone? What has to be fulfilled? Ataupun apa jawapan nak letak? You don't have to do any calculation, but just a sign. Extrinsic. Fatul says same. Bala says same. Betul ke same equal to? If your Ni is equal to Nd, is it extrinsic? Fada said more. Betul ke if your Ni is more than Nd, your semiconductor is Fada, you yang mana satu tu? Less or more? Ibu dua-dua tu. More pula. Okay. Bala said, you tukar fikiran Bala. Tadi you put equal, right? So way less, isn't it? I changed your mind. Page 1, okay, less. So for it to be extrinsic, remember kita approximate Ni is the intrinsic, so that's why the subscript I is very, very important. Ni shows your intrinsic carrier concentration. In intrinsic condition, and silicon and 10 to the 10, right? So if you're talking about extrinsic, your Ni has to be less than, at least. Ataupun you can also say way less than. It can be done as well. So, sorry, it can be done as well. You can either say less than or much less than, much lesser than. It can be done as well. It's okay as well. As long as your Ni is less than Nd, tapi for it to be more effective, it should be way less than lah. Be way lesser than, because you're comparing 10 to the 10 with 10 to the 14, for example. You kena get this right first, basic. Okay, this is extrinsic. So see the question is here is only notation. Simple je. Lebih ke kurang ke sama. Extrinsic, Ni has to be way less than your Nd atau Na, depending on N-type or P-type. But at high temperature, you get your change here. You get it to be intrinsic again. After demonstrating extrinsic in the middle region, you keep increasing the temperature, it's going to be intrinsic, because at this point, this relationship is no longer valid. And now you are getting your Ni to be approximately equal to Nd, or you can say equal to Nd pretty much. Okay. So now Ni equals to Nd is intrinsic, isn't it? Because you're going to get a lot of thermal excitation, which at some point will overcome the level of your doping level earlier on, okay, either Nd ataupun Na. So at this point, the inflection point here, okay, dekat sini, if you like the knee here, the knee region here, dekat inflection point, kat sini lah if you like, that inflection point, the change, this is where your thermal excitation overcomes your doping level, and your Ni can be approximated as Nd, and your Nd doesn't have any competitive edge at all. It doesn't have any advantage. Tak ada apa lah. Doping tu is like cancel out if you like, because Ni is just too much of thermal excitation at a very high temperature. Beyond this point, the semiconductor becomes intrinsic. Okay, the temperature at which the semiconductor becomes intrinsic depends on impurity concentration and the band gap value. Okay, depends on these two things: band gap value and impurity concentration. So at this point, Ni will overcome your Nd, and then if you go further, okay, at this point, Ni will be approximated as your Nd. What happens if you go to this point? In this region, what happens to the relationship between Ni box Nd? Anyone? Any guess? Against just a symbol to demonstrate your understanding. What do you think at this point? Apa symbol yang the accurate one that you can represent here? Anyone? At this point, Ni will be dash will be a blank Nd. Sama? Is it sama? Sama is a minimum case. Minimum, at least it has to be equal to, if you go for higher temperature, what do you think will happen, Vision? It has to be at least equal to, for it to overcome the doping level, for it to be intrinsic. If you go further and further and further at higher temperature, what do you think will happen? Yes, it will be more than at least. Okay, more than, or perhaps, I don't know, more than. This one is very relative. Either you're going to put 1 or you're going to put 2, depending on this. If it's easy to overcome your Nd, say your Nd is like 10 to the 13, kacang lah, nak overcome the Nd is like, you can do that at a very low temperature. I don't say low temperature as in room temperature ataupun freeze out. Relative low temperature, but perhaps you don't need up to 500 Kelvin, perhaps you need 400 Kelvin, say, in order for you to already observe that inflection point and it's going to go up. Macam lagi if your Nd or Na is lower, then it's a lot easier for you to overcome, isn't it? So you might need lower temperature for you to overcome your Nd or Na to be able to get to intrinsic region. Okay, but if your Nd or Na is way higher, say 10 to the 18, 10 to the 19, so of course it's going to be a higher temperature required for it to overcome. So now in this curve, we're talking about 10 to the 15 only, which is, well, not too bad, not too high, not too low. If you're talking about Nd of 10 to the 18, so you might need higher temperature for you to see that inflection point and for you to get into the intrinsic region. And that's what it means by this impurity concentration dependent and also band gap. If you go for higher band gap, then what do you think will happen? Okay, let's just finish it off with this band gap. Until next class kita discuss calculation. Tak sempat calculation. I just want to make you understand about this thing first, this concept first. How do you then compare this with band gap? If you're saying silicon is 1.12, and then if you compare that with, say, some other semiconductor with band gap of 1.8, for example, what do you think will happen to this graph? Will it be harder to overcome? Will it be harder to get to intrinsic, you think? This is analytical. Saya ajar basic, but then the question is pushing the boundaries. With whatever concept that you have understood, the theory you have understood, you have to stretch that a little bit to apply to some other materials, for example, with the very same knowledge. Do you think it's a lot harder, or it's a lot easier, or it's no change, or just no change in terms of the energy needed for you to overcome, to be able to get into intrinsic? What do you think? Silicon is 1.12 eV. If we switch that to a material X with band gap of 1.8. Right, Bala said it's a lot harder. What's your logic, Bala? Why do you think it's a lot harder? You can unmute yourself. Let's finish off with this.
It takes more energy to overcome the larger band gap to reach back to intrinsic region.
Okay, so it takes larger energy, isn't it? So kita discuss earlier on the concept of band diagram, kan? Your EV, your EC, your EG, and I gave analogy of minyak tak cukup masuk island and so on so forth, and you start in the middle of the bridge. You couldn't make it to the journey, you couldn't make it to the destination because the energy is not enough, right? And the same goes here. So if you're requiring more energy, if you're referring to the very same EV as your ground, if you like, so you now have your EC higher in the second material, so it needs a bigger amount of energy, a larger amount of energy to overcome the band gap in order to be successfully thermally excited. Okay, so you need to have a higher energy required in order for it to overcome, and therefore the very same thing as well. Okay, so we'll stop here and we'll do the today's what, Thursday, right? Tak ada class esok, right? So we'll do next Monday then. So please go through the calculations first. Today we have discussed about, we've revisited the concept of compensated semiconductors, and we've discussed on the dependency of your EF to the temperature and doping. Okay, and we've discussed about this notation, less than, equal to, more than, and this graph. Okay, walaupun the notation that we discussed now seems very simple, Ni versus Nd in different conditions, this single box punya symbol demonstrates a lot about your understanding. Either less than, way less, approximately equal, more than, way larger than, right? It demonstrates your understanding on the mechanism. Walaupun soalannya is very simple je, but it tells a lot. Okay, so hopefully we have discussed properly about that. And is there any question at all about this? Ataupun you're still confused on the items that we've covered today? Anyone? You better clear it out now, clear the air now if you don't understand, because next we're going to do the calculations, and then we're going to move on to the next chapter, which is a carrier transport phenomena. How do the carriers move, drift, diffusion, and then we're going to start talking about PN junction, majority, minority carrier concentration, Ni versus Nd, and we're going to use a lot of majority carriers, minority carriers in the original site, in the new site. When you talk about PN junction, you got to calculate the majority and minority in the original site, which is P's, let's say, and then what happens when the carriers have moved into the N side? What happens to the majority and minority at that point? And what happens to the carriers originally from the N side, now coming to P side? What happens to the majority and minority in both sides of the N and of the P? And this will govern the operation of your semiconductor devices eventually. That will cover in the second half with Dr. Marzaini. So at this point, any question? Can you understand? Tadi saya nampak ada a bit of confusion still based on your notation. So that's why discussion is very important. Okay, just a single answer tells a lot. Not to say that you don't understand and you tak faham ke atau whatever. That means I could have missed something, or something is not clearly explained, or I need to revisit the very same concept for you to move on, before you move on. Okay, so that's what it means. That's why it's very important to understand, to ask questions, to discuss, to do the calculations, so that you get things, together as a final puzzle. Okay, sekarang you tengah belajar all the jigsaw. You're combining here, you're learning there, and you're going to see things coming together as an equation, as an object eventually in this topic, in this course at the end. Okay, so any questions, any confusion? Yang mana tak tanya tu, I couldn't help unless you ask question, right? I can only assume that you understand, ataupun you can do your own revision to get to make sure that you understand, right? If you don't ask, then the best of my side is to assume, which is not wise, of course, that you are already okay, right? So, yep, from time to time we'll do discussion and ask question. So please attempt this calculation 1, 2, 3. We'll discuss some. I'm not going to go through the details of each. I want you to try out. So let's do this calculation on the next Monday, right? And then we'll move on to carrier transport phenomena, which is the next topic. I've uploaded already the notes on ELIT. Okay, so I'll see you again next Monday, inshallah. Bye bye. Take care. Assalamualaikum.